I'm going to write this e to the ikz somewhat differently so that you appreciate more what it is. So e to the ikz, I'll write it as square root of 4 pi over k. You say, where does that k come from? We'll see in a second. Sum over L, square root of 2L plus 1, I to the L, y L0, 1 over 2I. Basically, what I'm going to do is I'm expanding this JL function for large x. So I'm going to take this equation, and I'm going to expand it so that the argument is large, which means R is large. I want to describe for you those waves that are really going on here. So since the argument is KR, and you have a KR here, that's the origin of the K that I pulled out in here. And then you have e to the I KR minus L pi over 2 over R minus e to the minus I KR minus L pi over 2 over R. And this is valid for R much bigger than A. It's an approximate thing because we approximated the Bessel function. This is exact. This equation is exact for all R. But that equation now is not. That equation is showing you that you have here an outgoing wave, because it's e to the ikr minus and times e to the minus I et, the energy times time. So that's an outgoing wave. This is an ingoing wave. So this is ingoing, and this is outgoing. So I'm going to say a couple of things about this that are going to play some role later. It's a series of comments. Because this is a particular expansion, and due to the fact that this is a general expansion, you could say that this is an approximate solution of the Schrödinger equation far away, but in fact, each term, each value of L is an approximate solution. This is not an approximate solution because we added over many L's and somehow they help to create an approximate solution. This is an approximate solution because each L is an approximate solution. Because to get a solution, you could have said L is equal to 50, and that's all what I'm going to use, and that's an exact solution. And therefore, when I look far away, it will look like that with L equal 50, and that would be an approximate solution that can be extended to a full solution. So each L term here is actually independent. If you tell me a wave looks like that far away, I would say, good, yes, that's possible, and that comes from a solution. You're getting an approximate solution, and you could make it exact by turning the exponentials into Bessel functions. Even more, we will show, we'll discuss it a little later, I could get a solution that is approximate by considering either this wave or that wave. Suppose you just have the outgoing wave. The fact that the Schrödinger equation works for this one approximately doesn't require the ingoing wave. the Schrödinger equation doesn't mix, really, the ingoing waves and the outgoing waves. It keeps them separate. So this is an approximate solution, and this is an approximate solution as well. Every term here, independently, every L and every ingoing and every outgoing wave is a good approximate solution of the Schrödinger equation. Now, this is important to emphasize because this is called partial waves. So the term partial waves refers to the various L's that work independently. Now, to motivate what we're going to do, I'm going to go back to the case of one dimension, so that you need a map to orient yourself in the argument we're going to do now. So in order to understand partial waves and how they work, let's think about the one-dimensional case for a minute. I used to do that in 804. I don't know if has been done by other instructors, but we've done in 804 that stuff. So let me tell you about it and how it works in that case. So this is an aside 1D case of scattering. So in scattering in one dimension, one usually puts a hard wall at x equals 0. There's some potential up to x equals a. And then there's nothing. It's a finite range potential. So even in the case of d equal 1, you look for a solution when there's no potential. This is the v of x. This is the x-axis. If v is equal to 0, you would have a solution. Phi of x would be a solution, energy eigenstate. And would be sine of kx. This is the analog of our e to the I kz that we called it phi of r. Here you have a phi of x, which is a sine of kx, and it's your energy eigenstate. And that's a solution if v is equal to 0. If v is equal to 0, the wave must vanish at the hard wall at x equals 0. So that's your solution. On the other hand, we can also write it as 1 over 2I e to the I kx minus e to the minus I kx. And this wave is the incoming wave, and this is the outgoing wave. Very analogous to above, because this x is defined to be positive and plays the role of radius. In this problem, incoming means going down in x. Incoming in spherical dimensions means going down in r. So we're doing something very analogous. That's why the study of scattering in one dimension is a good preparation for the study of scattering in 3 dimensions. So you have an incoming wave and an outgoing wave, also because, again, there's an e to the minus I et over h bar. So here it is. What we try to do is to write a scattering solution corresponding to the same physics. So the scattering solution, psi of x, is the full solution is going to have the same incoming wave, because that's the physics that we're trying to understand. We put the same incoming wave, and we try to see what happens. That's what we do when we do scattering. So if we want to compare our solution to the case when v is equal to 0, we put the same incoming wave. But then solving the scattering problem means finding the outgoing wave, which now may be different. Because exactly when you have a potential, you have something in that you have control what you send in, but you have no control what comes out. That's solving the scattering problem. So the thing that you have here must be an outgoing wave, e to the I kx, with the same energy, because energy is conserved. We're talking about an energy eigenstate anyway, so it must have the same energy. And it must have the same probability flux as the incoming wave. So the magnitude of this wave and the magnitude of this wave must be the same. It almost seems like I have to write the same thing that I wrote here. But no, I can add one more little factor. It's conventionally written as 2I delta of k, a phase shift. Delta of k, an extra phase. And that's the claim, that's the whole thing. You have to solve what's going on here, but outside, and this is only valid for x greater than a, outside where the potential is 0, you must have that the solution is of this form. Here, this is for 0 potential everywhere, so this was valid everywhere, but in particular, it's also valid for x greater than a, and here we compare these two things. So this is the general solution for scattering here, and now we can also add another definition. We can say that psi of x is going to be equal to phi of x plus the scattered wave. Our intuition is that this wave here has the same incoming component as the reference wave. But nevertheless, it has the different outgoing component, and that's the scattered wave. It is exactly analogous to what we did here, in which we have the total wave being a reference incoming wave. Well, actually, incoming and outgoing wave, the e to the I kz has incoming and outgoing wave, and it's a solution when the potential is equal to 0. Just like this one, this phi. So psi is equal to 5 plus scattering wave. Here it is the scattering wave. It's purely outgoing because the incoming part is already taken care of. So a completely analogous thing. So let's solve for the scattered wave here. The scattered wave. So in this equation, we have 1 over 2I e to the I kx plus 2I delta k minus e to the minus I kx is equal to 1 over 2I e to the I kx minus e to the minus I kx plus psi s of x. Well, these two terms cancel. It is the fact that the ingoing waves are the same. And then I can subtract this other two to find psi s is equal to 1 over 2I. I can factor the e to the I kx. That tells me it's an outgoing wave. And then I have e to the 2I delta k minus 1. That's a term there. I think I got everything there. It's written, I'll write it here. There's a little bit of space. Psi s as e to the I kx, e to the I delta k, sine of delta k. I factor out 1 times I delta k. So this becomes e to the I delta k minus e to the minus I delta k that form together with the 2I in front a sine of delta k. So this is your outgoing scattered wave. That's the shape of the outgoing scattered wave in terms of the phase shift. Okay, so now we have to redo this in the slightly more complicated case of 3 dimensions and get it right. So that is our task. That's what we have to figure out how to do.